Okay, so let's compose f of g and g of f, starting with f of g of 1. When you first start with the composition, you look inside the brackets, looking at g of 1 here, then directly going to your g function, noticing that 1 is an x value, and then the y value for that particular point is 3. So g of 1, therefore, is simply 3. And then you go ahead, looking now at f of 3, identifying your f function, particularly the x value of 3. What is the y value? Well, the y value is 3. So the answer to f of g of 1 is 3. Similarly with f of g of 2, we go to our g function, we find 2, there it is. G of 2 is 2, so that's what we're plugging in here. As it turns out, we're going to plug that into our f function, so f of 2, well, that's 4. Therefore, f of g of 2 is 4. F of g of 3 is 4, f of 4 is 1, f of g of 3 is 1. Last but not least, f of g of 4, we go to g of 4 is 1, now f of 1, that's 2, f of g of 4 is 2. So f of g is equal to 1 comma 3, so the x that we first plugged into the g and then ended up with 3 as our final output there, so 1 comma 3, 2 comma 4, 3 comma 1, 4 comma 2. That is the final answer for f of g of x, is what we say. Moving on, g of f of 1, same type of thing. This time, of course, we're looking at f of 1. So f of 1 is 2. Therefore, now g of 2 is what we're looking at. We go to the g function. There's g of 2, which gives us an output of 2. Same thing, though, with now 2 plugged into the f function, g of f of 2. F of 2 is 4, so now g of that number, in this case g of 4, is 1. So 1 is your final answer there. Continuing on, g of f of 3 leads to 4. And lastly, g of f of 4, 3. So the final set notation of values for g of f of x is this. Moving on to example 2. Find g of h of x and h of g of x for g of x equal to 3x minus 4 and h of x equal to x squared minus 1. So the composition of g of h of x, or as you see here, the common notation, which I tend to use, as you see here, first up you take your h function, x squared minus 1. So x squared minus 1 is going to then be substituted into the g function for x. As you see here, the next step, they're noting that substitution by writing g of x squared minus 1. And then 3 times that quantity, as I'm showing here, x squared minus 1, and then minus 4, which stems from this. Do the math by distributing the 3. 3 times x is 3x squared. 3 times negative 1, negative 3, and then minus 4, negative 3, negative 4, negative 7. So 3x squared minus 7. H of g of x, very similar. In this case, though, we're substituting g of x into the h function. The g of x function is 3x minus 4, as you see here. That whole quantity will be substituted in for x into the h function. So as you see, 3x minus 4 in parentheses, yet again, quantity squared minus 1. Now, the step that I would like to show here, and us being very careful with the simplification of 3x minus 4 quantity squared, I'll write that as a binomial squared, so 3x minus 4 times 3x minus 4, and then minus 1. Well, it is a binomial squared, so we have to write it in this way. Foiling, of course, then has to be our next step. 3x times 3x, 9x squared. 3x times negative 4, that's negative 12x. Inside there is another negative 12x, so that adds to negative 24x. And then negative 4 times negative 4 is 16. We still have that minus 1, so don't forget to take 16 minus 1, leading us to 9x squared minus 24x plus 15. Now we'll ask us to take it one step further, if possible, and that is maybe factoring out a GCF. I can see that all three of these are divisible by 3. In other words, if we factor out a 3, we are left with 3x squared minus 8x plus 5. Okay. Now there is the possibility, of course, that this is still factorable. So when we attempt to see if it is in fact still factorable, it may be, it may not be, but let's take a look. So we know that maybe by guessing and checking our way through that the first two terms, 3x and x, if you FOIL just those two, you get 3x squared. And if we want to get 5 as our last term there, well, we can think of maybe putting 5 here, 1 there. 5 times 1 is 5. And then the sum of 3 and 5 will give us 8, but of course has to be negative, so we'll make those both negative. So we got 3x times x, 3x squared, 3x times negative 1, negative 3x, negative 5 times x, negative 5x, and then negative 5 times negative 1, positive 5. So this is the best final answer for this particular problem, fully factored. So let's continue and taking a look here at a couple of exercises. Okay, the exercises we'll take a look at will be number 1 here to start. For each pair of functions, f of g and g of f of x need to be found here if they exist. Starting with the f function, which has 3 ordered pairs, negative 1, 2, 5, 6, 0, 9, and the g function 6, 0, 2, negative 1, 9, 5. We'll go ahead and start with f of g of 6. Now I'm going to start with that because I know that 6 is an input for the g function. And in plugging in 6, we know that we get 0 as an output for that particular g function value. Plugging in now 0, if it exists, into the f function, which thankfully it does, leads to 9. And that's my first value. Next, we'll do f of g of 2. Yet again, 2 is an input for the g function, so I went with that next, which leads to negative 1 as its respective output. Then we look at the f function, and again, hopefully negative 1 is an input. It is, as we see, and the output for negative 1 is 2. So f of negative 1 there, 2. We'll go ahead and finish up with the last input for the g function, f of g of 9. G of 9 is 5. F of 5 does exist. It is 6. So we have all three answers there, which we'll then go ahead and simplify or write as f of g to be equal to 6, 9, 2, 2, and then lastly 9, 6. In the set notation that I do want, as you can see, this speaks to all of the respective ordered pairs, as we can see. Moving on to the composition of g of f of x. Okay, I'll go ahead and do that here. So g of f, the first function input for the f is negative 1, so we'll do f of negative 1 first. Turns out f of negative 1 is 2. So I'll take g of 2 then, if it exists, and it does, it looks like. 2 is an input leading to negative 1 in that g function. We'll go ahead and continue with then g of f of 5. F of 5 is 6. And then we take g of 6, which is 0, and that is my final. And then continuing with g of f of 0. F of 0 is 9. And then g of 9 is 5. So we really can write our final answer here. They all exist, as we can see. Now we can say that, well, negative 1 leads to negative 1, 5 leads to 0, and then lastly 0 leads to 5. Okay, that in full represents my final answer, the set notation as we know. Let's go ahead and continue with number 5. Okay, now with number 5, we are going to go ahead and take the composition of f of g of x. Okay, I'm going to write this notation this time, show some variety, and then I'm going to go ahead and show the same thing with g of f of x. In this particular notation. Again, there is another way we can write this, but I'll choose to do it in this way this time. So I'll do f of g. In other words, we'll take the g function and substitute that, which is right here, x minus 9, into the x variable, into the f function. So that becomes x minus 9 quantity squared plus 2 times the quantity x minus 9. Okay, again, that's just me substituting here and there. Notice I did leave it in parentheses, or put it in parentheses, which then in my next step speaks to the following. Got to FOIL those two. And I'll distribute now. 2 times x, 2 times negative 9 there leads to 2x minus 18. If I appropriately FOIL, I've got first x squared, outside negative 9x, inside another negative 9x, which leads to negative 18x, adding like terms. Multiplying negative 9 and negative 9 is positive 81. I still have those last two terms. I have like terms of negative 18x and 2x, which lead to negative 16x. And then 81 minus 18, or 63. This is my final answer of the composition of f of g of x. Moving on. Last problem. G of f of x. So we'll go ahead doing the composition like before. G though of x squared plus 2x. So we're now substituting x squared plus 2x in for x, which leads to this. X squared plus 2x and then minus 9, right? I'm plugging in that entire expression in for x into the g function. And the parentheses really aren't quite necessary, because in the next step I'm going to drop them out anyways, leaving me with simply x squared plus 2x minus 9. Now, as a final note, I do want to go back to a problem just to show that there is a possibility that the composition of functions may not exist. So in doing that, let's go ahead and take a look at number 2. Okay, so number 2. Again, very similar process as far as composing f of g and g of f. We'll go ahead and start off by taking f of g of 3. Okay, so if we take f of g of 3, okay, yes, there is an input of 3 for the g function, which leads to 7 as an output. And then we say, okay, well, we want to plug in 7 into the f function, but as it turns out, 7 is not an input at all for the f function. So when this happens, we actually can jump to the conclusion that this does not exist. DNE stands for does not exist. Okay, and that's as far as you need to take the composition of f of g. Now, as far as the composition of g of f, that can happen. All right, we'll do g of f of 5. Plugging in 5 gives you negative 2, and negative 2 gives you 6, so that will work. Plugging in 9 will work. Plugging in negative 4 will work, and plugging in 0 will also work. And without giving you the exact answers to g of f of 5, 9, negative 4, and 0, I will conclude this by saying that they will work.